Greetings to my AP Chemistry class. I want to start today by letting you know that we're going to be building off of Lewis structures by taking the Lewis dot diagrams that y'all were making over the past 2 days, and we're going to take them and determine the actual three-dimensional structure of the molecules. And to do so, we're going to be working with a simulation that I'm going to share with you so that you can actually play around with these. And then I'm going to have some for you to actually draw Lewis structures, build the molecules, and then see if you can actually identify their shapes. So we're going to be talking about Vesper theory, as it's pronounced Vesper, but it's valence shell electron pair repulsion theory, which says that the electrons in the outermost energy shell repel each other, and lone pairs of electrons repel even more than bonded or shared pairs. Then we can use that to predict molecule geometries. This is yet another application of Coulomb's law that electrons repel each other. And so what we're going to be looking at with this chart is the difference between is how this affects our basic framework of molecules. So the difference between lone pairs and atoms is a lone pair, it's the ones that are represented by the two dots when you draw the molecule, and atoms are obviously atoms. Now, it does not matter whether we're dealing with double bonds or triple bonds or anything like that for this, but we're going to be working essentially with 5 basic frameworks. We've got the linear framework, and I'll just kind of sketch this out for you. If I can launch the app, it has disappeared on me. So we have the linear framework is essentially if you just have two atoms, it's linear, obviously, because 2 points make a line. Or if you just have 3 atoms, they're all connected to the central atom. These two electron pairs would repel each other. For instance, especially if this was like double bonded here, and then we have some other lone pairs of electrons in a molecule like this. What matters is that these pairs of electrons repel each other and try to get as far away from each other as possible. So the angle here is 180 degrees. And all that matters for the shape of the molecule is what's happening with the atom that's in the middle. So we go back and look at some other examples. The next shape we have, once you get to 3 atoms attached to the central atom, we get to trigonal planar. So if we have an atom in the middle, then we have 1, 2, 3 things attached to it, then this is trigonal planar. It's a flat triangle where the bond angle between all of these, as you might could guess, is 120 degrees. And if we look at the molecule shape simulator and we fire this up, we can actually build some of these, and you'll actually get to play with this and see what they look like. So if we just play with a model, this shows you have 2 atoms, everything gets attached to the central atom, everything gets as far as possible from each other. If you have 3 atoms, it makes this flat triangle, the 120 degree bond angles. This is trigonal planar. Our next framework is if you have 4 things attached, it is tetrahedral. So if we have 4 things attached to the atom in the middle, I'm just using X's to represent generic atoms, then this becomes tetrahedral. And this is where we have a limitation of we're drawing a 3-dimensional structure on 2-dimensional paper. This bond angle is not 90 degrees, it's 109.5 degrees. So if we look at a model of this one, this brings us to 109.5. This is a tetrahedron. This is the Tetrahedral Framework. Then if we add a fifth atom to the middle, or to the atom that's in the middle, then we get to Trigonal Bipyramidal. This one has some really funky bond angles. Let me redraw this a little better to help visualize this. This one has some really interesting bond angles associated with it, and I'm going to try to represent this as best I can in 2 dimensions when it's a 3-dimensional object. If I add another one, we are now at what's called Trigonal Bipyramidal, where you have what are called the axial atoms. That would be the one up here at the top and the one down here at the bottom, where these bond angles are 90 degrees and 90 degrees. So they're 120 degrees apart from each other. And then we have what are called the equatorial atoms, which are 120 degrees apart from each other. So there are 2 separate bond angles that exist in this molecule. So if we look here, the way I'm trying to draw this one is that these are the axial ones, and then these are the equatorial. You can maybe visualize that. And then if you think about this, if we add a sixth atom to the middle, then we get what is called octahedral. So we add yet another one. This is octahedral. Everything is 90 degrees from each other. So we still have axial and equatorial positions, but it doesn't really matter because everything is perfectly symmetrical. Whereas with if we only have 5 atoms attached to the middle, it's not that way. We have 2 different bond angles going on. So this is the basis of all of the shapes. And if we look at what's called the electron geometry, that's the same for everything that we've built so far. Octahedral, trigonal bipyramidal, tetrahedral, trigonal planar, and linear. Where things get different is if we start introducing lone pairs of electrons. This is where you're going to maybe want to make some notes of these shapes and playing with these simulations as much as possible until you can actually visualize these shapes in your head is going to be of some critical importance. Because if we go to this one that's trigonal planar, if we substitute a lone pair of electrons in there for one of the atoms, now the shape is bent. So this is bent. Now, this is showing a very idealized bond angle here. In reality, we remember from the previous slide, says that lone pairs of electrons provide even greater repulsions. This bond angle would probably be a little bit less than 120 degrees, more like, say, 118 or 117 degrees. This is a trigonal planar framework with 3 things attached to the central atom, but the shape of the molecule, we just focus on the atoms, is now bent. If you substitute 2 lone pairs of electrons, obviously you're back to just linear because anytime you only have 2 atoms, the only shape you can make is line. So that's it for the trigonal planar geometry. The tetrahedral geometry gets a little more interesting. So with the tetrahedral geometry, if we replace one of these atoms with a lone pair of electrons, now the shape becomes trigonal pyramidal because it kind of makes a triangle-based pyramid shape. And the bond angle here, because this lone pair provides extra repulsions, is typically going to be a little bit less than 109.5. So for instance, if I switch over to some real molecules and I pull up a real molecule that actually exists, NH3, the bond angles are 107.8 degrees. It's not 109.5, it's a little less than that. So this is the trigonal pyramidal shape that you should be able to identify. And if we replace a second atom with an electron pair, now we end up with the bent shape. So keep in mind, this is not a flat molecule. These molecules, these electron pairs here versus those atoms down here, it's bent. It's not a 90-degree angle. It's less than 109.5 in the real world. The most prominent example of this being a water molecule, where the bond angle is 104.5 degrees. So that's the different shapes we can build with the tetrahedral framework. So let's go back and take a look at the Trigonal Bipyramidal framework. Now, what's interesting here is if we substitute a lone pair of electrons for an atom, the lone pair of electrons is always going to go into the equatorial position because it has greater distance from more of the atoms near it. If it goes into an axial position, like this atom up top here, that atom up top is 90 degrees away from 3 different atoms, as opposed to if it goes in the equatorial position, it's 120 degrees away from 2 and 90 degrees away from only 2 atoms instead of 3. So all the substitutions go in the equatorial position. So if I remove an atom and substitute in a lone pair, it's gone into the equatorial position. And this makes for a really fun shape. This shape is called seesaw because if you ignore looking at the lone pair, it's still there, but I'm just hiding it from you. This kind of looks like a seesaw, like the... Oh, let me see if I can rotate this back around. Kind of looks like the children's toy, a seesaw, where you can kind of rock back and forth like that. So that shape is called seesaw. Yes, the scientists are really that original when they come up with the names. Just wait for the next one. If we put in a second lone pair of electrons, then we end up with this shape, which is called T-shaped. So you can see T-shape down here because it looks like the letter T. And if we substitute in a third lone pair of electrons, now all of a sudden this molecule is linear with 3 lone pairs of electrons wrapped around the axis. So it's a really interesting scenario. Let me see if I can find one of these over here for you, maybe. Yeah, the xenon difluoride. It's a linear molecule, but it's not your traditional linear shape because we have these 3 lone pairs of electrons wrapped around the central atom. And then that's all we can really do for the Trigonal Bipyramidal framework. So now we're going to look at the last framework, the Octahedral Framework. I suppose I should have mentioned the reason this is called Trigonal Bipyramidal is because it's 2 triangle-based pyramids that are stacked together so that their bases are attached to each other. That's where the shape gets its name. And the octahedral, it gets its name because if you were to fill in the sides of this and make a 3-dimensional shape out of this, it looks like an octahedron. So octahedral is the shape name. On this one, if we substitute in a lone pair, it doesn't really matter where the lone pair goes because all of these positions are equivalent to each other. So we sub in a lone pair. This shape is called square-based pyramid because now, if you kind of ignore the lone pair down there, it makes a square-based pyramid shape. If we put in a second lone pair, what's important is that the second lone pair will go opposite the first lone pair to minimize the repulsions of the lone pairs. So it's going to go on the complete opposite side, like this. And so this makes a really fun shape. This is called square planar. It's called square planar because obviously it looks like a square and it's flat. So these are the different shapes. And what you're going to need to be able to do is draw a Lewis structure and then be able to identify what shape it is. So a major task for you today is to play around with this simulator as much as possible and substitute in and start making some shapes. We don't need to know any of the other shapes like this version of T-shaped. That's not one that you really need to familiarize yourself with because it's not going to come up. I don't know of any actual molecules that have that. A good place to start is by looking at these examples on the real molecule side and just seeing if you could draw their Lewis structures and see how these shapes match up with the Lewis structure that you've drawn. Because it's going to be a major part of the AP exam that you're able to match a Lewis structure with a shape, because the shapes are going to tell us a lot about the properties of the molecule. And you don't have to memorize these exact bond angles in real molecules like 84.8 or 104.5. You just need to know that if there's the lone pairs, it will make this bond angle a little less than you would expect.